Welcome to this lecture number 21 on this NPTEL course on fluid mechanics for chemical engineering undergraduate students. The topic of our discussion in the last lecture, lecture number 20, was differential balances. Differential balances are balances of mass, momentum and energy that are written down for a fluid, okay, and these are valid at each and every point in the domain of the fluid. So, the advantage of using differential balances is that one can, after solving the equations that come out of differential balances, one can get a detailed description of the velocity and pressure distributions in a flow field, such as flow in a pipe or flow past a body like a sphere or an airplane wing. So, while it has the most exhaustive and accurate information that one can get for a fluid flow, but the downside is that the solution of these differential balances are not easy, and often one has to use a computer, a very powerful computer, to solve the equations that govern the mass, momentum and energy for at each and every point in the fluid. But these are the most rigorous equations that one has for describing fluid flow. So, it is useful to know and have a good feel for how these equations are derived and how they are simplified to get some solutions that are often used in many applications. The other approaches that we already discussed, is that of integral balances. In integral balances, we do not write down equations that are valid at each and every point in the flow domain. Rather, we write down, we choose a very huge control volume, which encompasses many equipment such as pumps and turbines and so on, and one writes the overall balance of mass, momentum, energy. So, the integral balances are fairly simple, but the point is the use of the integral balances will involve quantities such as viscous losses or forces on solid surfaces, which are not known a priori. So, one is left with a rather incomplete set of equations, because one does not know in general what are the losses. So, one is often left with the choice of neglecting certain important features like losses in order that one can solve the integral balances. At times experimental data is available to estimate these losses. So, one can use them or, as we will see a little later, by solving the differential balances in simple systems, one can actually find out the losses. Okay. So, the basic idea in differential balances is that one takes a very tiny control volume of infinitesimal size. So, let us try to draw, for simplicity, a cubic control volume. So, you have 3 Cartesian directions. Okay. Let us draw it slightly short. Okay. Okay. You have x, y and z, 3 orthogonal directions, and the distances along the 3 directions are simply. So, this is simply delta y, and this is delta x, this is delta z. So, the volume of this infinitesimal control volume is delta x delta y times delta z. Okay. And we are going to take an infinitesimal control volume in the sense that we are going to eventually take the limit of delta x, delta y and delta z going to 0. So, essentially this control volume will shrink in the limit to a point, and thereby we are going to derive equations that are valid at each and every point in the fluid. Since we are taking the limiting process of delta x, delta y, delta z going to 0, we can anticipate that we can get differentials of various quantities. So, that is why we use these balances are called as differential balances. Okay. So, what one does is to derive the differential balances is to use the integral balance for a CV and take the limit of an infinitesimal CV. So, if we look at mass, conservation of mass as applied to a CV, we already derived the rate of change of mass present in the CV plus integral rho v dot n dA over the control surface is 0. This is the most general equation that governs mass conservation for a CV. Now, we are going to apply this to this infinitesimal CV. Okay. So, apply to the infinitesimal CV with sides delta x, delta y, delta z, the cubic CV that we just drew here. Now, few simplifications arise when we apply a general conservation equation such as this integral balance to a CV. First of all, since let us look at term by term. So, if you look at this term, okay, if you look at this term, now since the CV is so tiny, the variation of density within the CV can be neglected to a first approximation. So, we can pull this out of the CV. This is approximately this in the limit of this CV volume tending to 0. Okay, we can write this very easily, and this is nothing but if you integrate this volume, you will simply get times delta V, where delta V is delta x times delta y times delta z, the volume of the CV. So, that is one simplification that comes in the first term. Even if you look at the second term, we can do some simplification. Okay. Now, since the CV cross sectional areas are so small, okay, we can assume uniform flow. Okay. So, we can simply write this as summation over all outlets. For outlets, V dot n is positive, remember, is V for outlets and minus V for inlets. This is something that we had seen before. Okay. So, I times rho. So, let us now the key thing is that if you pull, if things are uniform, we can pull this outside the integral, okay, and integral over dA will simply give you A, the area of cross section through which fluid is flowing. So, we will give rho A, rho I A I V I out minus rho I A I V I through all the inlets. Now, we have a CV like this, a simple cubic CV, and x, y, z. This cubic CV has 6 faces, okay, one at x, okay, one at x plus delta x, okay, another at z plus delta z, other at z, one at y, one at y plus delta y. So, there are 6 phases at various stations. Okay. Now, therefore, fluid can come in and go out of any of the 6 phases. Just for the sake of clarity, we are going to assume that fluid is going to enter, for example, the phase at y. This is the phase at y. Sorry, the phase at let us say the phase at x, and it is going to leave the phase at x plus delta x. That is, fluid is entering the phase at x, okay, and fluid is leaving the phase at x plus delta x. Okay. So, this is so we made a small mistake here. Okay. The phase at x, so this is the coordinate x, the phase at x is here, the phase at x plus delta x is here. Okay. So, that is what I have drawn here. The phase at x is the left side of the CV, the phase at rise at x plus delta x is here, the right side. So, fluid can enter through this and leave through this. Okay. Well, you can also have that the fluid entering through this and leaving through this, or both sides, fluid entering through both sides and leaving through some other phase. That does not alter any of our derivations, because we are going to assume the velocities to be algebraic quantities, that is, they have sign associated with them. So, accordingly, in a given problem, they will take plus or minus signs accordingly. Okay. But just for the sake of clarity in derivation, we are going to assume that fluid is coming in through here and leaving through that. So, we had this equation d rho dt times delta V plus summation I rho I A I V I over the 3 outlets minus rho I A I V I over the 3 inlets. Okay. This is what we are going to use to derive the equation. Okay. Now, to do that, first of all we have to account for the amount of mass that enters at x, and then we have to find out the amount of mass that leaves at x plus delta x. Okay. So, in general the quantity such as rho v will be functions of x, the velocity vector will also be a function of x, because we have used the continuum hypothesis, and many all fluid quantities such as rho v, p, pressure, rho density, velocity, pressure, they all vary smoothly and continuously with spatial coordinates. So, we will have to evaluate in order to find out the mass flow at x is equal to rho a times the x. So, velocity is a vector, it is u times I plus v times j plus w times k. So, this is the x component of the velocity evaluated at phase x. Mass flow at x plus delta x is rho a u at x plus delta x. Now, in general rho a u at x plus delta x is not the same as rho a u at x, although a is the same if you assume that the cube area is not changing, but rho and u in general are not same. Okay. So, first of all, what is a? A is equal to, in this phase, delta y times delta z. Here also a is delta y delta z. So, the mass flow, mass in at x is rho u times delta y delta z evaluated at x. Mass out at is rho u delta y delta z at x plus delta x. This in general not the same as the quantity rho u at x, but you can use what is called Taylor expansion or Taylor series expansion to find out what is rho u at x plus delta x. This is rho u evaluated at x plus d dx of rho u evaluated at x times delta x plus half d dx squared d squared x dx squared times delta x squared plus so on. Now, we are going to drop all the higher order terms. Okay, so, we are going to restrict only to this order. So, if you want to write down and likewise you can write down other directions, mass in at y is rho v delta x delta z at phase y, mass out at y plus delta y is rho v delta x delta z at y plus delta y, and then mass in at phase z is rho w delta x delta y, mass out at rho w okay. Now, we are going to use this equation d rho dt plus summation over all outlets rho a v minus summation over inlets rho a v is 0. So, d rho dt plus, now let us look at all the 3 phases separately. For the phase at x, the outlet mass flow rate is rho u at x times delta y delta z my plus d dx of rho u at x, sorry, let's delta y delta z times delta x, that is the Taylor series expansion. Okay. We are neglecting higher order terms, minus this inlet flow rate in the x phase, which is rho u at x times delta y delta z. Similarly, you can write down for other two phases plus rho v at y delta x delta z plus d dy of, after having Taylor expanded, rho v at y delta times delta x delta z times delta y. This delta y comes from the Taylor expansion, minus the inlet, which is rho v at y times delta y delta z, plus the z phase rho w at z times delta z, sorry, delta x delta y plus d dz of rho w evaluated at z times delta y delta x delta y, okay, times delta z, which comes from the Taylor expansion, minus rho w z times delta x delta y is equal to 0. Now, we can see that several terms are going to cancel away. For example, these two terms will cancel, these two terms will cancel, these two terms will cancel, leaving us with only this term. Now, if you see, all these terms are multiplied by the volume, and sorry, this term is also multiplied by the volume, if you remember, which we wrote earlier. This delta v is nothing but delta y delta z and times delta x. So, you can divide the entire equation by delta x delta y delta z to give a simple expression for the mass conservation d dx of rho u plus d dy of rho v plus d dz of rho w is 0. Now, this equation is valid at each and every point in the fluid. Okay. This is also called the continuity equation or equation of continuity. Okay. Now, we also wrote down a coordinate free vector form of this equation. This form of the equation is valid only in Cartesian coordinates. Okay, Cartesian reference frame. Okay. Now, if you want to write it in general other coordinates, in other coordinate frames, we will use the property of a gradient or a divergence, okay, to write this as follows, and this is a vector form which is coordinate free form. So, once you know what are the properties of divergence in other coordinate systems, you can use this form and write down the equation of continuity in other coordinate systems, while you cannot use this form in other coordinate systems. That is only valid for Cartesian coordinate systems. Okay. So, having said that, we proceeded further to use this continuity equation to simplify it for an incompressible fluid. Before I do that, I can write this equation as d rho dt plus v dot del rho plus rho del dot v is 0. If you expand this, term, you get two terms, okay, by using differentiation by parts. Now, this expression combined together is the substantial derivative of density plus rho from this term del dot v is 0. This term is this. Okay. The substantial derivative of any quantity is the rate of change of that quantity with time as you follow a given fluid particle. Okay. Whereas, this term is simply the rate of change evaluated at a fixed point in space. Okay. Now, for an incompressible fluid, d rho dt is 0. Okay. Suppose you follow a given fluid parcel, okay, its density will not change with time for an incompressible fluid. So, if you knock this term off for an incompressible fluid, we get the continuity equation for an incompressible fluid to simplify as rho times del dot V is 0, but since rho is a non-zero constant, you have this is the equation of continuity for an incompressible fluid. Continuity equation for an incompressible fluid. It is important to understand that the time derivative goes not because the flow is steady, it is because of the fact that the substantial derivative of density is 0 for an incompressible fluid. So, this is valid for both steady and unsteady flows of an incompressible fluid, both unsteady and steady flows. Of an incompressible fluid. So, that is something that is important for us to remember, that this equation is in general true for both steady and unsteady flows, but it is applicable only for an incompressible fluid. We also saw that incompressible condition is valid when, in the last lecture, I will not go through this again, when the velocity, typical magnitude of the velocity relative to the speed of sound is very small, that is the ratio of V over C is very small compared to 1, that is the Mach number is small compared to 1, then the flow is incompressible. If you want to know the derivation, you please refer to lecture number 20, the previous lecture. I will not derive this here again. Okay. So, for this course will be predominantly focusing only on incompressible flows, wherein the density of a fluid parcel does not change as you follow the fluid parcel. So, our continuity equation will always take the form of del dot V equal to 0, that is the velocity field. The velocity is a vector quantity and it varies at each and every point in space in general in a flow, but what this means is that del dot V equals 0 means is that the velocity field vector field has no divergence, okay, in an incompressible flow. The velocity can vary at each and every point in space, but in such a manner that the divergence of the velocity vector always has to be 0. Okay. This is a very rigorous and important constraint on the possible values which the velocity vector can take, because it cannot take any arbitrary values, it always has to satisfy the continuity equation del dot V equal to 0 for an incompressible fluid, because it is essentially a statement of conservation of mass. So, it is a very fundamental principle that no flow can violate. Okay. So, although we cannot show individual applications of continuity equation right now, what is important for us to understand is that the continuity equation must always be satisfied by any fluid flow, and for an incompressible fluid it takes a simple form that the divergence of velocity field is 0. Okay. Now, we are going to go further, proceed further, and we are going to introduce the notion of a stream function. Okay. Now, I am going to assume again incompressible flows. For incompressible flows, we always have del dot P is 0. In general, fluid flows, the velocity vector, velocity is a vector, can have component in the I direction plus component in the j direction plus a component in the k direction, that is the z direction. Okay. But we will restrict our attention now to what are called 2D flows, that is only these two components are non-zero. We can choose the coordinate frame in such a manner that the z component of the velocity is 0. So, the flow is invariant. 2D flows means flow is invariant in the z direction, okay, z direction, and this is first point, and the z component of velocity is 0. Okay. If you do this, so you have only these two velocity components. u and v. The continuity equation for Cartesian coordinates for an incompressible fluid del dot v equal to 0 means partial u partial x plus partial v partial y plus partial w partial z is equal to 0. So, this is del dot v is 0, but since we have said that w is not there, it is a 2D flow, it is an incompressible 2D flow. So, the continuity equation simplifies to, or the mass conservation equation simplifies to partial u partial x plus partial v partial y is 0. Okay. So, and both the components of velocity u and v are functions of only x and y. Because we are saying that, assuming that the flow is invariant in the third direction. Now, we are going to introduce a concept, new concept called a stream function. It is a function of the two independent variables, it is denoted by the Greek letter psi, it is a function of both x and y, and it is related to the fluid velocities in the following manner. Okay. So, it is related as follows: u of x y is partial psi by partial y, v of x y is minus partial psi by partial x. That is, this new function is constructed, is defined in such a manner that if you take, and it is a function of both the independent variables x and y in a 2-dimensional flow. If you take the partial derivative of the new function with respect to y, you get the x component of the velocity u, and if you take the partial derivative of the new function psi with respect to x, that is the negative of that is basically the y component of the velocity v. So, this is the definition of stream function. What is the advantage of this definition? Now, let us look at the continuity equation. You have partial u partial x plus partial v partial y is 0, that is the continuity equation. Now, I am going to substitute u here and v here through these definitions. So, you get partial x of partial psi partial y plus partial y of minus partial psi partial x is 0. Okay. That is the continuity equation. Okay. Now, I can pull this minus sign out. So, you get partial squared by partial x partial y psi minus partial squared by partial y partial x psi. Okay. This is the continuity equation, but partial squared psi by partial x partial y is actually partial squared psi by partial y partial x, because the order in which you take the partial derivative should not matter for a continuous function of two variables. So, this means that an important conclusion can be drawn, that the continuity equation is automatically satisfied by the definition of the stream function. By the definition of the stream function. So, this is a very important conclusion, because now we are finding that by constructing the stream function in this fashion, by defining the stream function in this fashion, you are automatically satisfying the continuity equation for 2-dimensional incompressible flows. That is a great simplification, because when you want to proceed further to momentum balance, you will find that you will have two sets of equation, the mass balance and momentum balance, which are linked with each other, or they are coupled to each other. But by defining the stream function, you are doing away with one equation, you have to solve one equation less, and it is always nice to solve a lesser number of equations than more number of equations, mathematically speaking. So, in that sense, the stream function is very helpful in the solution of 2-dimensional incompressible flow problems. Okay. So, it is a purely mathematical reason as to why this this motivation of stream function is purely mathematical, that of course, it simplifies the solution of equations by reducing the number of equations by 1. Okay. So, that is one motivation for introducing the stream function. Another motivation for the stream function is that we have to first understand that stream functions are related to, we are going to show functions are related to streamlines. We had discussed streamlines long back when we discussed fluid kinematics. Kinematics, if you remember, is a description of flow without worrying about what are the underlying causes of the flow, that is the forces acting on the fluid. So, there we define streamlines as lines which are always parallel to the fluid velocity vector. Suppose you have fluid, okay, let us just first draw the fluid velocity vector. Suppose you have at each and every point the velocity vector is pointing in this direction. Okay. We can connect at each and every point a line that is tangential to the fluid velocity vector, and such a line is a streamline. A streamline is tangential to the tangent to the fluid velocity vector at each and every point in the flow. Okay. So, if you have a local velocity vector v, okay, and the displacement along the stream function is dx, and if these are parallel, then the cross product of v cross dx is 0. This is something that we did it last time. We did a few lectures back when we did kinematics. Okay. Now, this gave rise to the condition, if v cross dx is 0, okay, then we found that u dx, we found that dx by u is dy by v. This is something that we derived by using the fact that there are two vectors, the velocity vector and the displacement vector along the streamline, they are parallel. So, the cross product of these two vectors should be 0. That gave rise to this equation. So, along a streamline, we can say that u dy minus v dx is 0. Okay. This is along a streamline from the definition of streamline. Now, I am going to use, okay, the definition of stream function, that u is partial psi by partial y dy, v is minus partial psi by partial x. There is also one more negative sign, the two negatives will make a positive, partial psi by partial x dx is 0. So, along a streamline, okay, we are finding this relation. Okay. Now, if you know little bit of calculus, you will realize that if psi is a function of two variables x and y, then the variation in psi, a small variation in psi that occurs because of small variations in x and y, can be written as partial psi by partial x at constant y times dx plus partial psi by partial x, partial psi by partial y at constant x times dy is 0. Okay. This is I am not saying it is 0, this is the variation in psi because of variations in small variations in x and y, but we find from the definition of a stream function that along a streamline, from the definition of a streamline, this quantity is identically 0. So, d psi is 0 along a streamline. This is something that we just found because this is valid along the streamline, and this is nothing but d psi, the total change in psi that is incurred if you change. So, d psi, if you change x by a small value and y by a small value. So, if d psi is 0 along a streamline, what this means is that if you go along a streamline, okay, psi has to be a constant, because along a streamline, if you change the variation in the stream function, it turns out to be 0 rigorously. So, psi is a constant along a streamline. This is a very major result, because if you want to plot streamlines, all you have to do is to plot lines of constant psi. Once you have the information of how psi varies as a function of x and y, psi is a function of two variables for a two dimensional flow, then we can simply plot constant values of psi and those will be streamlines. So, this is a very useful result, because if you want to plot fluid flow behavior, if you want to visualize fluid flow behavior, it is often useful to use streamlines to do that, both experimentally as well as from a computational point of view. In that context, it is much easier to find out the streamlines by just drawing lines of constant psi. Okay. So, this is one another use of stream function. So, we found two uses so far of a stream function. Firstly, the stream function simplifies the solution of problems for two dimensional incompressible flow situations, because by defining the free stream function like the way we defined just few minutes before, we found that the incompressibility condition is identically satisfied. So, you are left with one equation less in your solution scheme. So, it is always helpful from a mathematical point of view. The second advantage is more physical, that if you find a stream function, then lines of constant stream functions are streamlines. Now, streamlines are special lines in a flow domain where the velocity vector, the streamlines are always parallel or tangential to the velocity vector at each and every point in the fluid. So, by plotting the streamlines in a flow domain, it is easier to have a visual understanding of what the flow is going to be like. Okay. Now, there is another important third major implication of using stream functions, and that relates to the volumetric flow rate that flows between two streamlines. Okay. So, let me explain this a bit slowly. Suppose you have a flow domain, and we are anyway restricting ourselves to 2D flows. So, you have a 2D flow domain in the xy plane. What we mean by 2D flow is that the variation along, suppose you have x, y and z, the variation along the third dimension z, this is x, okay, is less, very less. So, there is no variation in the third direction. Okay. So, that is the meaning of saying that the flow is two dimensional. So, the another use of stream function is the fact that the difference between values of stream functions between any 2 points in a flow domain has some relation to the volumetric flow rate that flows in between the two streamlines. Okay. So, we first saw that lines of constant values of stream function denote a streamline. So, let us imagine a two dimensional flow. In any case, our discussions are now restricted to 2D flows. So, you have let us say 3 stream functions, 3 streamlines, 1, 2 and 3, okay, and each streamline is denoted by a constant value of stream function psi 1, psi 2 and psi 3. Okay. Now, the claim is that, and remember that the flows are 2 dimensional in the sense that there is no variation in the third direction z. So, these streamlines are almost like sheets. So, in the third direction, okay, and there is no variation, because you can always construct many such streamlines, okay, in the third z direction, and there is no variation of any quantity in the third direction. So, you can cut at any cross section and they look like lines. Okay. Now, suppose if I look at any 2 points, okay, A, B, okay, you can ask the question, what is the volume of fluid that flows between these 2 points per unit width of the third direction z. Okay. And you can likewise consider some other orientation of the area. What is the amount of fluid that is flowing between, volume of fluid that is flowing between this area per unit width in the third direction, okay, per unit time. Okay. So, that is the question that we want to answer. So, let us find out the volumetric flow rate. Okay. So, the volumetric flow rate, first let us use the line AB. The line AB is actually a surface, because you have to extend it in the third direction, and since things are invariant in the third direction, z direction, we can calculate everything per unit width of the third direction. Okay. For the volumetric flow rate per unit depth, let us say the third direction across this surface AB. Now, I am choosing this surface AB, okay, because in this surface, okay, along this surface AB, the surface is directly perpendicular to it is perpendicular to the x axis. So, the only component to the velocity vector which is going to cause flow towards this surface is the x component, because the y component is parallel to the surface. So, it cannot cause any flow. So, the volumetric flow rate is nothing but integral. Okay. In principle, it is V dot n times dA. Okay. Now, in principle, but since it is unit width, we cannot write dA. Okay. So, we have to write it as some let us just write it as some okay, let us just write it as dA per width. And for this simple system, since V is purely along the x direction, V dot n will become u, okay, and the coordinate for integration is simply dy per unit width of the third direction. So, you do not have to worry about the third direction. So, q is simply integral a to b u dy. And what is the differentiating thing between points a and b? It is the y coordinates. This is y1, this is y2. So, this is simply y1 simply equal to y1 to y2. Instead of u, I can put partial psi by partial y dy. Okay. So, q is nothing but psi at y2 minus psi at y1. Okay. So, and psi at y2 is simply psi 2 and psi at y1 is psi 1, because along each and every point in this line the stream function is a constant psi 1. Okay. I can do this for the surface or lines BC also. Okay, let us do that for the line BC. Okay. Q is integral. So, if you look at this diagram, now this is completely perpendicular to the x, it is completely perpendicular, the unit normal is perpendicular to the y direction, is along the y direction, and the surface is completely normal to the y direction. So, the only component of velocity that is going to contribute is the y component of the velocity. So, the normal component is just the y component. Okay. So, q will be written as per unit width will be written as. Now, the only thing that differentiates between these two points between B and C is their x positions. Here it is x2, here it is x1. Okay. So, integral x1 x2. Okay. So, we are now computing the point x1 here and x2 here. Okay. Volumetric flow rate between these 2 points, V dy, V dx, because the area of it is going to be integrated along the x direction. So, dx, V is nothing but minus partial psi by partial x dx. So, this is psi of x1 minus psi of x2. Now, psi of x1 is psi 2, because x1 lies on this psi 2 line, psi of x2 is psi 1. So, this is nothing but psi 2 minus psi 1. Okay. So, what we have shown is that by choosing two different completely different areas, we have shown that the amount of fluid that flows between these 2 points is the same as the amount of fluid between flows between these 2 points. So, if you take any orientation, okay, the amount of fluid that flows between these 2 points per unit width of the third direction per unit time is always given by the difference in the value of the stream functions between those 2 streamlines. So, the difference in values of the stream functions between any 2 streamlines directly gives you a measure of how much volume of fluid that is going to flow between those 2 points. Okay, between those 2 points. So, what is the big advantage of this description? The big advantage of this description is that suppose you have a stream as a fluid flow pattern like this. Okay, these are streamlines. So, these are values of streamlines psi 1, psi 2, psi 3, psi 4. Okay. So, along at each and every point along this streamline, okay, psi is constant psi 1. So, if I take psi 1 minus psi 2, the difference, okay, it is constant from here to here, okay, because it is the same streamline, the same 2 streamlines, but here the width, the distance between those 2 streamlines is much more compared to a point like here. Okay. So, if the difference between 2 points, the 2 stream function values is related to the volumetric flow rate. Okay. More amount of volume, the same amount of value has to flow between these 2 points as well as these 2 points, because psi 2 minus psi 1 is constant. That means that the velocity here will be less compared to the velocity here, because of the fact that these 2 streamlines are converging. So, by immediately having by having a quick look at the streamline distribution present in a fluid flow, you can immediately say where the fluid velocity is going to be larger and smaller, because the difference between values of stream functions between any two streamlines is always equal to the amount of volume that is going to flow across any line drawn between these two streamlines. Okay. Since psi 2 minus psi 1 is constant along the streamlines along any 2 points along the streamline. So, whenever the 2 streamlines converge, we can immediately conclude that along at the point of convergence, the velocity vectors will be much greater compared to the points where the streamlines are diverging. So, this gives rise to a very quick aid for flow visualization, because once you have a huge data, let us say from a computer solution or an experiment, in fact, by plotting all the data in terms of streamlines, one can immediately get a qualitative feel as to where the flow velocities are large and where the flow velocities are small. Okay. So, this is the big advantage of differential stream function. So, just to recapitulate what we did in today's lecture. Okay. We first derived the most general form of continuity equation for a Cartesian coordinate system, that becomes the following. Okay. This is for Cartesian coordinates. Now, we can also write this in vector form, which is coordinate free. That is, the nature of the equation that we are going to write in the vector form is coordinate free, is independent of the coordinate system you choose to work with. It is always the same. It is also called the abstract form, d rho dt plus del dot rho v is 0. Now, in many applications you will see little later that it is often convenient to use coordinate systems that correspond to the symmetry of the particular system. We may be interested in flow through pipes or flow past a sphere, in which case it may not be convenient to work with Cartesian coordinate systems, and it may be beneficial for us to use a cylindrical coordinate system or a spherical coordinate system. In a cylindrical coordinate system, any point is denoted by r, which is the distance from the origin to the projection of the vector in the xy plane, theta, which is the angle the projection makes with the x axis, and z, which is the normal z coordinate in the Cartesian coordinate direction. So, you have r theta z in cylindrical coordinates. Okay. Now, just so in Cartesian coordinates, the continuity equation or the mass conservation equation in the differential form becomes this. But suppose you in a cylindrical coordinate, the velocity vector is written as v r e r plus v theta e theta plus v z e z. Okay. So, if you want to write the continuity equation, we cannot write by by just extending the continuity equation in the Cartesian coordinates. This is wrong, because for the first reason that this equation is such a straightforward extension of the Cartesian continuity equation in cylindrical coordinates is not even dimensionally consistent, because this is an angle variable. Theta is an angle, it has no dimensions, it does not have dimensions of length, whereas all r and z have dimensions of length. So, clearly you cannot readily extend this to more other coordinate systems such as cylindrical and spherical coordinate systems. A more fundamental reason is that if I look at the abstract form, it becomes divergence of rho v. Now, divergence in the cylindrical coordinate system is 1 over r okay, plus E theta 1 over r d d theta plus E z d d z. This is a gradient operator dotted with rho v r E r plus rho v theta. Okay. So, plus rho v phi, sorry, rho v z E z. If you do this operation, key thing for us to remember is that in cylindrical coordinates, okay, if I look at the r direction and theta direction, this is E r, E theta is along this direction. Okay. If I move along the theta direction, you can see that E r is going to change its direction. So, E r is not independent, it is not always pointing in the constant direction. If you change theta, E r varies. Okay. So, this is a very generic feature in curvilinear coordinates, wherein the unit vectors will change the directions as you go along a given coordinate direction. Okay. So, unlike in Cartesian coordinates, where the unit vectors I, j, k are always pointing the same direction regardless of no matter where how you vary x, y and z, that is not the same. So, essentially the crux of the matter is that when you take the divergence, you not only must take the divergence of V r, but also E r, E theta and E z, and this will give rise to a different kind of equation. So, I will not do the details, but it is important to know that in cylindrical coordinate systems, okay, the continuity equation will become the following. Okay. So, one cannot readily extend the Cartesian continuity equation like here to cylindrical coordinate systems, because of the fact that unit vectors themselves will vary with spatial coordinates in curvilinear coordinate systems. So, that is something that we must keep in our mind, and the same thing applies even for spherical coordinate systems. Okay. Having done that, we introduce the notion of stream function, which is very useful, especially when you consider two dimensional flows, because you need not satisfy the incompressibility equation or continuity equation separately, because the stream function by definition satisfies del dot v equal to 0. So, that is one big advantage of using a stream function for two dimensional incompressible flows. The second advantage is that by the stream functions, if you plot lines of constant values of stream function, they are exactly the streamlines. Remember that the streamlines are always locally tangential to the fluid velocity vector. So, it is a very useful way of visualizing fluid flows. The third important result that we derived is that the difference between two stream function values between any two streamlines gives you a measure of the amount of volumetric flow rate per unit width in the unit depth in the other direction, okay, for two dimensional flows. So, this also helps in flow visualization, because when the streamlines are far apart, okay, and if they converge at some point, that also means that the velocity vectors magnitude of the velocity will be increasing wherever the streamlines are converging. So, these are the these three are very important implications of the definition of stream function. So, this really completes our discussion on differential mass balance, which gave rise to the continuity equation. The continuity equation is extremely fundamental, because it always must be satisfied, but it cannot be solved in isolation. We have to combine it with linear momentum balance as well as energy balance. So, we have to go to the next step of deriving the differential momentum balance for fluid flows, which we will do in the next lecture.